Okay, so as an undergrad physics student, you've probably had exactly one absolutely unbreakable rule drilled into your head since day one, right? Nothing, literally nothing, travels faster than the speed of light in a vacuum. It is the absolute speed limit of the universe, the total bedrock of causality. But if you were paying attention to the physics headlines back in the 90s and early 2000s, you probably felt this massive sense of cognitive dissonance. I mean, we had major headlines declaring that this ultimate speed limit was broken. Light pulses were somehow exiting mediums before they'd even fully entered them. No way, right? Well, today we are going to completely dismantle that impossibility. Welcome to this explainer, where we're going to fundamentally reshape how you think about time, causality, and what it actually means for a wave to travel.
Real quick, here's our syllabus for today. First, we'll hit the faster-than-light illusion. Then, we'll break down the freight train analogy. After that, preserving the speed limit, manipulating phase and power, and finally, we'll wrap up with reshaping time in audio.
All right, diving right in. Section 1, the faster-than-light illusion. How in the world did two completely separate, super rigorous experiments manage to seemingly break the fundamental laws of nature? Let's take a look.
So, check out the contrast between these two setups. Over on the left, we've got L.J. Wang's incredibly famous 2000 experiment over at Princeton. They fired a laser pulse into a specially prepared chamber of glowing cesium atomic vapor. And through a really wild process called anomalous dispersion, the peak of that light pulse actually appeared to exit the glass chamber faster than the speed of light. Like before the tail of the input pulse had even fully entered the chamber. Wild, right? Now, on the right side, about a decade earlier in the 1990s, Raymond Chiao's team at UC Berkeley pulled off a similar trick using glass prisms separated by just a microscopic air gap. Photons hit the first prism, decayed, and then instantly tunneled across the gap to the second prism in what looked like absolute zero time. Two totally distinct environments, two completely different mechanisms, but the exact same illusion, a massive, blatant violation of causality.
But here's the thing you have to remember. Nature doesn't just break her own rules. As physicists in training, you know that when the data contradicts the foundational laws of the universe, you don't throw out the laws, you need a paradigm shift. To solve this paradox, you actually have to stop viewing a photon or a light pulse as a single, isolated point particle just zipping through space. Instead, we have to start analyzing the envelope, the overall shape of the wave itself.
Which brings us to Section 2, the freight train analogy. This is the core mechanical metaphor we're going to use to demystify these crazy optical illusions.
Think of a light pulse, a wave packet, not as one single solid thing, but as a super long freight train rolling across the landscape. This train isn't just a giant block of metal. It's actually constructed of dozens of distinct individual freight cars all coupled together. Now, in physics terms, these individual cars represent the distinct frequencies that make up your wave packet. They travel together, and collectively they create the overall shape or the envelope of our train. Keep that image in your head.
Okay, so watch what happens when we run this train through a dispersive medium, kind of like that cesium gas chamber we talked about earlier. Imagine this medium as a highly complex switching station. When our frequency freight train rolls into the station, the medium selectively messes with it. It aggressively detaches the rear cars, basically tossing them into the darkness. In wave mechanics, that's the attenuation of the trailing edge. But simultaneously, and this is the crazy part, it pulls brand new phantom cars to the very front of the line, completely amplifying the leading edge. The station is physically and dynamically rebuilding the train while it's still moving.
And honestly, that brilliantly explains exactly why those optical instruments were totally fooled. Because the rear cars were dropped and new ones were magically added to the front, the overall center of gravity of our train shifted way forward. The peak of the pulse, essentially the middle of our newly arranged train, passes the station much earlier than it would have if it just chugged along normally. The medium reshaped the envelope so aggressively that the instruments, which are just mindlessly tracking that peak intensity, registered it as traveling faster than light.
Section 3, preserving the speed limit. Sure, the peak arrived early, but does that actually mean information traveled faster than light? Let's dig into the math that proves causality is still perfectly intact.
This inequality right here, you want to etch this into your brain. Signal velocity, v sub s, must absolutely always be less than or equal to the speed of light, c. So while the group velocity, which is the peak of our wave packet or the center of our train, can technically be measured as exceeding c because the envelope got reshaped, the true signal velocity, that hasn't changed at all.
And why is that? Because the true signal velocity isn't the middle of the train. The signal velocity is the very front edge of the locomotive engine cutting through the air. In wave mechanics, this is that split second, the very first moment the intensity rises above zero. Physicists call this the point of non-analyticity.
And the thing is, the dispersive medium, no matter how much it scrambles or reshapes the cars behind the engine, literally cannot accelerate that initial point. Information, the true start of the signal, is strictly bound by the speed of light. So breathe easy. Causality is completely preserved.
Section 4. Manipulating phase and power. Now that we've safely secured the laws of quantum optics, let's pivot to the gritty history of power engineering. Because, believe it or not, reshaping waves is definitely not just some 21st century parlor trick. Let's trace this timeline for a second. Long before lasers and atomic vapors, engineers were already manipulating raw power. Back in the 1930s, massive industrial currents were controlled by these intense devices like the mercury arc valve and the Ignitron. We're talking liquid metal and precision-triggered plasma being used to lock perfectly onto the phase of an alternating AC sine wave. Then, as we roll into the late 20th century, we see analog notch filters being used to differentially attenuate frequencies in audio and radio circuits. And today, we replicate those exact same phase shifts using C++ in modern digital signal processing. The really big takeaway from that 1930s industrial plasma bridge is pretty profound. By triggering a plasma arc at a very specific moment in a wave cycle, those early engineers were essentially practicing phase angle control. It was basically our very first proof that if you master the phase of a wave, you can fundamentally alter how energy behaves over time. You can reshape that temporal envelope without ever having to break the laws of physics.
And that brings us to Section 5, Reshaping Time in Audio. This is where we connect those quantum illusions and industrial power grids straight into something you interact with every single day.
Okay, get this. The exact same physics that created that faster-than-light illusion in the cesium gas, it entirely governs the audio processing in the music you're listening to right now. The phenomenon is called negative group delay. The math you're looking at, T sub g equals negative d phi over d omega, basically shows how reactive components in an analog circuit, things like capacitors and inductors, store and release energy. At specific frequencies, the phase just violently shifts. The circuit differentially attenuates those frequencies, literally reconstructing the sound so that the peak of the output envelope actually happens before the peak of the input. Just like our freight train, the center of gravity of the audio wave is shoved forward in time.
Now, in the digital realm, we handle this a bit differently. Digital processors use what we call IIR filters, infinite impulse response, to exactly replicate that strictly causal analog math. It's just crunching numbers to push the output envelope forward. But digital processing also gives us a literal cheat code, the FIR filter, or finite impulse response. By intentionally delaying the entire audio system, basically introducing a global look-ahead latency, we actually grant the processor access to the signal's future. It gets to analyze the wave before it mathematically even needs to output it. This allows for perfect, linear phase manipulation without any of the messy distortion you get in analog systems.
So let's tie this whole thing together. Whether a wave is quantum tunneling through a microscopic air gap, passing through a chamber of glowing atomic cesium gas, or just getting processed by lines of code inside a silicon chip, the illusion is completely identical. As physics students, you know for a fact that we cannot change the speed of reality. That locomotive engine, the true point of non-analyticity, is never, ever going to exceed the speed of light. But by manipulating phase, we become the absolute masters of the envelope.
I really want to leave you with this final, kind of provocative thought. We've seen how physics puts strict boundaries on our physical world, yet it still allows for these totally mind-bending temporal illusions through phase manipulation. So, if a simple global delay in a digital architecture gives an audio processor literal access to a signal's future, how else might we start manipulating the envelope of time, especially as our reality becomes more and more dictated by digital architecture? Keep analyzing the shape, guys, not just the point. Thanks so much for joining me on this explainer, and I will catch you in the next one.